All right, last time we started talking about gerrymandering, which is the process of drawing the district's maps to favor something. So there are a few motivations for this. It could be to favor the incumbents, it could be to favor some racial group, and what we're going to be focusing mostly on today is situations where it favors one party over another. Typically, if you see some news article about gerrymandering, the main picture is going to be of some district in that map that looks especially bad, especially non-compact. And last time we talked about different ways of measuring compactness, and that can certainly be a useful thing to measure. So if we put restrictions on the map makers, if we say, hey, you aren't allowed to have any districts that have a score worse than something, then we're limiting some of the extreme cases of gerrymandering. We're somewhat hindering the ability to skew the whole picture one way or the other. That said, given modern computers and algorithms that can do these things, it ends up no longer being necessary to have strange looking graphs in order to accomplish similar goals. So today, rather than focusing on looking at a map itself or at a district itself and calculating some compactness score, we instead want to focus on the effect. In a famous Supreme Court case in 1996, the Supreme Court declined to overturn a potentially gerrymandered map, and one of the comments that Justice Kennedy wrote was that he didn't want the judicial system to be in a cycle of endless beauty contests. And what he meant by that was that he didn't want the courts to be in the business of judging the authenticity of a map based off of things like compactness scores. And that's actually a reasonable objection to some of the arguments with that. Certainly wish that the courts would do more to limit things like partisan gerrymandering. But as it turns out, focusing on the compactness of a district by itself isn't necessarily enough. So today instead, we're looking at the effect of a particular map. What is the end result after the election? What do we see? So in 2016, in all of the House races across the state of Pennsylvania, the Republican candidates won collectively 53% of the vote versus 45% of the vote for the Democrats. Okay, so that year, the state went a little bit more Republican than Democrat. However, if you look at the actual results, out of the 18 races, Republicans ended up winning 13 of the congressional seats to only 5 of the Democratic seats. So the results far more heavily favored the Republicans than the actual votes. It's tempting, at least for me, to just look at this one picture and say, hey, this is evidence that the game is rigged for the Republicans, so there must have been some gerrymandering, there must have been some nefarious foul play afoot. That said, we shouldn't immediately jump to conclusions based off of just this information, because there are reasons why the seat share percentages should have a greater difference than the vote share percentages, as we'll see in just a moment. Rather than working with complex real-world maps right off the bat, like the state of Pennsylvania, let's work with a simpler example like Squaretopia. So the idea here is that this is representing the state of Squaretopia. In this state, there are 100 precincts or regions. So when we actually draw things like districting maps, we typically don't zoom down all the way to the single building level. It's actually zoomed out a little bit further to what's called the precinct level. We can think of this as neighborhoods or counties, these indivisible blocks that we're not going to break up into pieces. So here we have a total of 100 precincts in our state of Squaretopia, and our goal is to draw a total of 10 districts. So we might draw a district like this. So that's one district, and then we can draw the rest of them, and depending on where we want to draw these lines, that's designating a particular map. What we don't want to do is cut across these precinct lines. We wouldn't draw a district like this because it does weird things to it breaks some precincts up across multiple districts. Instead, we're saying every precinct has to be entirely contained in one district. That said, we still have quite a bit of flexibility here. We could say that our districts are all of the columns, maybe all of the rows, or really any sort of combination like that. So in class on Wednesday, I'll have you work through some districting plans to try to gerrymander this in favor of one party or the other. So if we have a district like this left column, and there is some election, in this case, yellow would win 6 of the votes, uh, purple would only get 4. Therefore, for that district, the yellow party would win. So we can look across all of the districts in a given map and ask how many seats are won by each of the two parties, the purple party and the orange party. When you start drawing these lines yourself, you'll see that you have quite a bit of power to rig the game in favor of one party or the other, the orange party or the purple party. Much of your ability to do so has to do with the fact that the citizens of Squaretopia are very segregated. In the yellow precincts, they vote entirely for yellow. In the purple precincts, they vote entirely for purple. And even after that, the yellow precincts tend to cluster together and the purple precincts tend to cluster together. Let's imagine a different distribution for the state of Squaretopia. We'll keep the fact that 40% of the voters vote for the orange party and 60 vote for the purple party, but let's shift this to a more uniform distribution. So here we have a whole bunch of dots, purple and orange, that the idea is to represent that if we draw any particular district, in that district, 40% will be orange and 60% will be purple. And it doesn't matter then what shape our districts are. It doesn't matter how we draw those districts. It's always going to be the case that the split is 60 to 40. So if you look at any one district, even if it looks pretty gerrymandered, in that district, purple wins 60 to 40. So purple wins that district. Purple wins every district 60 to 40 because of this uniform distribution. In other words, the gerrymanderers don't have really any power in this distribution. Purple is always going to win every election. In practice, neither of these are quite right. The political party distribution is neither completely spread out evenly across the state or across the country, but at the same time, we also aren't completely segregated. We don't have precincts that vote entirely for one party or the other. So in practice, we are somewhere in between, and because of that, we have a mixed effect. Again, if the parties are distributed entirely uniformly, then the minority is always going to win 0 seats. Even if they win some percentage of the vote, no amount of seats will be won, and this isn't due to gerrymandering. It doesn't matter how we drew these. Even if we were trying to rig the game in favor of orange, orange would still win 0 seats in this uniform example. If the parties were completely segregated, then we might imagine a fair map to be roughly proportional. That said, in reality, people are distributed somewhere in the middle. A typical distribution of voters has a mix of these two properties. So even if we had a fair map, we wouldn't expect the percentage of seats won by the minority to be the same as the percentage of votes that they got. We don't expect proportionality. We actually expect the minority to do a little bit worse than that due to this effect of this uniform distribution. So if we go back up to our Pennsylvania example, we see that the number of seats that the Democrats won is lower than the percentage of votes that they got. But maybe that's something that we at least somewhat expect because voters within Pennsylvania are somewhat distributed. Maybe this type of discrepancy is to be expected. Well, since I already said that this was an example where the map got thrown out, we might suspect that, hey, this discrepancy is more significant than it actually is supposed to be, and as we'll see in a moment, that is actually what's happening here. The point that I'm trying to make is that we need a little bit more than just saying, hey, these proportions don't add up. Here's a way of asking a slightly deeper question. This is called the seat votes curve. We'll be comparing the percentage of votes that a party gets to the percentage of seats that they win. So in our running example, the Pennsylvania Democrats in 2016 won 46% of the vote, so 46%, but only earned 28% of the seats. They got 5 out of the 18 seats. So we can represent that with this point here. So great, this is what happened. This doesn't necessarily tell us anything new, anything beyond what this information does. So let's bring in some more information. Here's the breakdown of all 18 districts and how the election went. So what I'm recording here is the percentage vote from the perspective of the Democrats. So the Democratic candidate won District 1, 82% to 18%. We're just representing that by saying the Democrat won 82%. What we want to do for our seat vote curve is to ask a hypothetical question of what would have happened if the Democrats had done a little bit better. they only won 46% of the vote. What if instead they won 47% of the vote? Does that change the picture at all? So the way that we'll work this is we'll just say, all right, out of the 18 districts, what if every one of them increases its percentage by 1? So let's imagine that in District 1, the Democrat won with 83% of the votes. District 2, the Democrat won with 91% of the votes. In District 4, the Democrat lost, but this time earned 35% of the vote, etc. We're adding 1 to this column. Well, that's not going to flip any of the districts. None of these results are going to change. None of these numbers are going to surpass 50 if we only add 1. So we can expand our seat vote curve a little bit. We can extend this point to the right by a tiny amount, by 1%. I like to think of this as a dial that we're turning. We're gradually increasing the percentage of the vote that the Democrats won until we actually see a change. If we increase all these numbers by 2, nothing happens. By 3, nothing happens. But if you look at District 8, District 8 was won by the Republican because the Democrat only won 46% of the vote. So if the Democrats won 4% more, then they would have won 50% of the votes across the state. And that's the cutoff point where if they won a tiny bit more than that, they would have won District 8 as well. So we represent that by continuing our edge, continuing our graph to the right until we get to this 50% mark, and then jumping up a notch. So at 50.01%, then the Democrats will have won 6 out of the 18 seats. And we can continue turning up the percentage that they won until we see another jump. So this District 8 was the first point, or the first district that flips if we are increasing the Democrats' vote across the board. But if we increase even further, if we increase by a total of 7, both District 6 and District 16 will flip. So at a +7 to the Democrats across the board, we are at 53% across the state. That corresponds to an increase of 2 seats. If we continue turning this dial up and also turning this dial down, we can expand our seat vote curve to look something like this. There are a few artifacts or problems with this picture. Namely, on the ends, we have a weird effect because we had a few people run unopposed. This line continues all the way across when normally, if the Democrats are winning 20% more than usual, they probably would end up winning all of the seats. But if we look more in the middle of this picture, if we focus on this portion of the seat vote curve, this can illustrate any biases that the particular map might have. So notice that the seat vote curve doesn't pass through the center of our graph. So the center corresponds to the situation when a party wins half the votes and gets half the seats. That seems like an inherently fair thing to have happened. Notice that even if the Democrats did a little bit better, rather than getting 46% of the votes, they got 50%, they still would not have gotten 50% of the seats. In this hypothetical case, if they won 50% of the vote by shifting everything up a little bit, then they still would only win 6 out of the 18 seats. This distance is known as the partisan bias. So the partisan bias is the percentage of the seats under or over 50% that you get if you win 50% of the vote. So remember, all of this is hypothetical except for our one real data point. But it's a reasonable thought exercise to go through to say, all right, well, what if this happened? And if the Democrats in this election had won 50% of the votes, they would have not quite won 50% of the seats. So that discrepancy, that difference between 50% and the amount that they actually won, 6/18 or a third, that distance, that discrepancy, that 16%, is the partisan bias. So in this case, the partisan bias would be approximately 16%, which is a lot. So partisan bias, or the measurement of this vertical discrepancy, is a way of determining exactly how biased is a particular map towards one group or the other. We wouldn't actually expect this curve to always go through the middle. given the randomness of the world, it's certainly believable that, hey, we don't quite get to this exact middle. There's always going to be some partisan bias. So one question that we'll have is, well, is 18% partisan bias significant? Is this enough for us to say that, hey, something weird is happening? Well, that's a question for next time. I do want to say that there are several other metrics for determining how gerrymandered a particular map might be. One of which is, rather than saying, what's this vertical distance, is that we can ask the horizontal distance. The vertical distance was saying, if you won 50% of the vote, how much different than 50% of the share of seats do you get? We could instead ask, well, what percentage of the vote do we need to get in order to win 50% of the seats? In our hypothetical example, we were turning the dial and saying, oh, well, what if rather than 46% of the vote, the Democrats had won more? How far do we have to go until they get to 50% of the seats? And because this point in our seat vote curve is to the right of the center of this graph, that means that the Democrats need to win more than 50% of the vote in order to win 50% of the seats. This is called the mean median score. We're asking how much more or less than 50% of the vote is needed in order to win 50% of the seats. Whereas the partisan bias was a measurement of this vertical distance. This is the partisan bias. The mean median is a measure of the horizontal distance. It's called the mean median because a way of calculating this is by comparing the mean and the median of the vote shares. There are many other metrics out there, like the efficiency gap, which measures how many wasted votes each party has. But for the most part, all of these metrics agree when it comes to identifying a particular map or particular districting where there is gerrymandering. So some amount of variation between exactly normal is expected, but when we have particularly extreme scores in things like partisan bias, mean median, or any of these other metrics, that can be an indication that there was, in fact, some gerrymandering, that the map is rigged beyond what's expected for a particular party.